I mean, it's probably just a cold, but you know. Better safe than sorry, I suppose. All right, so I guess the first thing I should ask, is there any questions about the homework that I've assigned? Okay. So in that case, oh man, I didn't bring my, somebody here have a calculator? We'll need a calculator. Okay, good. So I want to look at some applications of right triangle trigonometry, right? And let's see here. So an example. All right, so suppose you're over here, and we'll neglect your height. All right. Here, I'll put you in a hole. That way we won't have to neglect the height. Now, there we go. So for some reason you're standing in a hole so that your line of sight is just with the ground level, all right? And suppose you know that this distance is, what would you guys want to make it be? 1,000 feet, let's say. Sound good? 1,000 feet. Right? Then you can talk about, and this is a building, right? Listen. Probably not enough windows. And then suppose that the angle of elevation, all right, what's the angle of elevation? Angle of elevation to the top of the building from your vantage point, the angle of elevation would be this right here, right? All right, and suppose you measure that, right? You've got some surveying equipment and you have like a little laser and points up there, and you look at your little protractor in the we really should make a protractor part of the required materials for this course, right? I should have done that. I was going to go buy you guys some at Walmart, but then I found out they're like $2 a piece, and then I was like, eh. It's not so much that I don't want to buy you something for $2, it's that I don't believe a protractor should cost $2. Like, it should have been $1, you know? I should have gone back to Walmart when they had the like clearance and gotten them for 50 cents or whatever. You got one, good. Oh no, I don't need it. It's fine. But I'm just saying, you know, the way these the surveying equipment works, right? Or at least one kind is it kind of has like basically a protractor built in, so you can measure the angle up off the horizontal, right? So there's equipment that can do this, and let's suppose because I'm going to be lazy, that this is 30 degrees. So then the question is, this is all, everything so far, this is this is given. All right, given. So the question, how tall the building? So what do you guys think? How would we do this? Cosine of theta. Well, let's see here. Let me draw a triangle down here. We're trying to figure out what this is. Let's call this thing y, all right? I'm going to call it h for height of the building, h, right? This is theta. This is 1,000 feet, right? We don't actually know the line of sight distance, right? And we can't calculate it either because it involves what we're trying to find out, you know? So which trigonometric ratio is the right tool for this problem? Tangent, right? Because tangent involves the opposite and adjacent side, but not the hypotenuse. We don't know the hypotenuse. Tangent's the right choice here. So we can say tangent theta, right, is opposite, which in this case is h, divided by 1,000 feet. So what's h equal to? H is equal to 1,000 feet times the tangent of 30 degrees, right, which is equal to 1,000 feet times the sine of 30 degrees divided by the cosine of 30 degrees. Now, of course, at this point, you could have used your calculator and told me the number. Do you want to do that? Tangent of 30 is 57?
Tangent of 30 is 0.57735.
So the tangent of 30 is 0.57, approximately. Now, I think that makes sense. The reason I do is this. The tangent of 30 degrees is sine 30 degrees over cosine 30 degrees, right? Now, we know those. Those are special angles. Sine of 30 is a half, and cosine of 30 is the square root of 3 over 2. The halves cancel, and you've got 1 over the square root of 3. So that's about 1 over 1.7 something or other, which is about 0.57 when you reciprocate it. Does that make sense? Anyway, if I had more common sense and grabbed my calculator on the way to class today, I could have just punched it in and got what? Approximately 570 feet, right? So I personally think that's pretty neat, right? Because it would actually be quite a pain to go to the top of the building and, you know, find a 570-foot long measuring tape and kind of drop it down, right? Or string or whatever. But instead of that, you can use trigonometry to figure out a missing side to a triangle. Right? In fact, this is how most of surveying works, right? Yeah. And this is also how we can tell, similar principles allow us to calculate the distance to astronomical bodies if we have partial information and can find like the distance between things. We can use, I think, what's called parallax, and it's also based on trigonometry. It's like one of the ways we figure out distance to like the moon, things like that, is based on these kind of trigonometric ideas. Let me see if I can come up with another example. How about this? You have a redwood, all right, and you know that the height of the redwood is 350 feet, right? Here's the question. How far would you have to stand from the base of the redwood, right, for the angle of elevation to the top of the redwood tree to be, what angle you want to pick? Let's not do a special angle. Let's do 50 degrees, right? I mean, it doesn't matter. So my question is, how far do you have to stand from the base of the redwood tree for the angle of elevation to be 50 degrees? So what's this? So there you go. This is what's given. Let's see if we can solve it. Now, what did you guys say? What should we use? Is this also a tangent problem? But this time, we're missing the adjacent side, right? So we still got tangent of 50 degrees is equal to h over x, which is 350 feet over x. to be careful how I talk, because if I talk the wrong way, it's going to throw me into this horrible coughing fit that none of you want to see. So, solve for x. What do we got? 350 feet divided by the tangent of 50 degrees. What do you guys calculate using your handy dandy? 193.68. There. I mean, okay, anyway. See, this is the kind of geometry you might want to think about, if you're building a house or something and planting trees away from it, and if you don't want to be able to see what's behind the trees, you think about how tall do they have to be away from your house to like shield the mountains behind it or whatever it is you're trying to cover up. Maybe more likely there's a building, right? And your house is here, right? And you want to plant a tree right here so that you can't see that building, You could use this kind of reasoning to figure that out. Of course, you could also just kind of draw a triangle, right? Anyway. Okay. Let me see if I can come up with a more complicated example. Let's see here. Suppose you have a building, all right? And on top of that building, there is a antenna tower, right? All right? And you measure that the angle of elevation, so you're, let's say, 1,000 feet away. Let's say 2,000 feet away, okay? You're over here, right? And you happen to know, the antenna is, let's say, 300 feet tall, right? Suppose you're given that. You know you're 2,000 feet from the base of the building, right? Oh, rats. I'm having a hard time coming up with complicated problems. My bad. Suppose you measure that angle of elevation to be what? Let's say 35 degrees, all right? Well, this will do. Then the question is, how tall is the building? We're again ignoring the height of Mr. Top Hat, all right? Think of him as an ant. All right, so what we can do is think about two triangles, right? Well, we can just think about this triangle, right? This has the height of the building, which we'll call h, right? And then this is the antenna height, right, which is what, 300? We know what? We know this adjacent side is 2,000 feet. And we also know that this is 35 degrees. right? It's the same thing, just there's a little bit of algebra here this time, right? So we do tangent of 35 degrees. Opposite, which in this case is h plus 300. If you don't mind, I'm not going to write the feet. Divided by 2,000. I'm just going to omit feet and put them back at the end, okay? Let's see here. So we multiply both sides by 2,000, right? And that gives us h plus 300 equals 2,000 times the tangent of 35 degrees. So solve for h. What do we got? H equals 2,000 times the tangent of 35 degrees minus 300, whatever that is, feet. $300 what? 949. Let me think about that. That makes sense, I think. If you just kind of picture it in your mind's eye, because 30 degrees would be a little bit lower, right? And, well, shut up. Let me not try to do it in my head. Today's not the day. All right? Any questions? No, it's okay. I don't want to contaminate your stuff. It's okay. I'm content to have you guys punch buttons. It's fine. Classroom interaction, right? All right. So I think if you understand these three examples, you can solve pretty much all of the examples that are in section, 1.6? They're all kind of this, more or less. All right. Now, there's another interesting kind of example in terms of radian measure that I think is good. And I was meaning to bring, I have a globe I'll bring in someday, and we'll talk about how to find the distance on the Earth using latitude and longitude. I think that's kind of interesting. So we should talk about that someday, but I don't have my globe with me, so you'll forgive me if I don't do that today. So I reserve the right to find a more horrible example of applications and bring it back to you at a later date. I feel like, I don't know, to me these are too simple. But if you also feel like they're too simple, then that's great. I mean, my question is, you don't have to say they're too simple, but do you think you guys could work these problems? All right, okay. Now, Professor Giles has expressed her enthusiasm for the new book, the other book, because the other book does degrees first and then radians, all right? Now, I haven't taught this before, but as a student, my own personal, the way I'm geared, like I don't want to have one day on degrees and one day on radians. I want to have one day on both so I can understand how they're different and related, so that's the way I taught it to you guys. But I'm like, on the other hand, Professor Giles has taught this many, many moons. She knows things that I don't know about the students. So I'm like, what's the problem with radians? And then she said, fractions. And then that resonated with me because there is a lot of students who have trouble with fractions, right? So perhaps this is a useful exercise for us. Let's just take a second and talk about rapid fire lightning round. I'm going to state the theta in radians. I want you to give me the degrees. How many degrees? I heard 90. Not once you say it, you're not allowed to answer another one. Pi over 4. What's that? What did you say? 180. Nope. You still have another chance. What's that? 45, right, 45 degrees. How about this? Theta equals to 3 pi over 4. Yeah. 135. Now, let's see here. Here's the way I think about that. Convert the pi to 180.
It was the formula converted 180 over pi.
That's, I mean, you're,
Pi will cancel out, and you're left with 3 180 over pi.
I mean, you're not wrong. The pi radians is equal to 180 degrees. So that's actually a useful guide. Just take the pi and the radian and replace it by 180, and that gives you the number of degrees. So 0.75 times 180 is 135, right? All right, how about theta equals to 2 pi over 3 radians? 120? Yeah, 2/3 of 180, 120 degrees. Right. Let's see here. Continuing with this rapid fire here. Find theta between 360 degrees and 720 degrees coterminal with theta equals to pi over 6 radians. Let me draw a picture. So first of all, pi over 6 radians, how many degrees is that? Augustina, you want to go with this one? No? Okay. Don't make me laugh. This is on you. This is your fault. 30 degrees, yes. So this is 30 degrees, right? Great. We want to find a coterminal angle between 360. So what do we have to do? You want to take theta and take 30 degrees plus 360 degrees times some number, right? Times some number such that this, whatever you choose, that's going to make it between 360 and 720 degrees. I mean, you're trying to select and to make it so. The way to solve these kind of problems is to guess, right? And n equals to 1. Basically, just add 360, right? So add 360. So the coterminal. So 360 plus what? 30. 390 degrees. Well, no, I said between 360 and 720. So if you wanted to do radians, you could add 2 pi. If you wanted it to be between 2 pi radians and 4 pi radians, you would add 2 pi radians. Look, so what's going on here is we have choices to describe the angle, right? We can add or subtract any multiple of 360, and it's geometrically the same direction, right? But conceptually, they are different, right? I mean, to get to 30 degrees, I just swing up 30 degrees. To do 390, my concept of that is to go around once and then 30 degrees more, you know? So they are different. But they do point to the same direction. That's why they're called coterminal. Okay. So I'm hoping that the homework I've assigned from the early sections in the book, if you work it out, it should eventually make you comfortable with these kinds of problems. All right? All right, now that we have finished that little walk down memory lane, let us go to chapter 6. Now, if you have a graphing calculator, in some sense, this whole exercise is a little bit silly. But, I mean, yes and no. You don't want to be reliant on the graphing calculator here. We want to be able to graph sine and cosine, just and simple modifications of sine and cosine, just using like basic templates, all right? So let's talk about the graphs of sine and cosine. All right, so let me remind you, what was our starting point? We have a unit circle, right? You got your x, you got your y. You take a point on here, right? And that point is, by definition, cosine theta, sine theta, right? That's how we define sine theta and cosine theta at standard angle theta. So we can also think about, you know, f of x. Well, I mean, I can say f of theta. Let me start f of theta to start with. F of theta equal to sine theta, right? And g of theta equal to cosine theta. I mean, these define functions, right? Functions of theta, right? The domain of f and the domain of g, everything, because of that coterminal idea. So the angle keeps sweeping, round and round and round it goes, clockwise or counterclockwise. Counterclockwise positive, clockwise negative. But we can consider cosine and sine of any real number of radians. So the domain of sine and cosine is the reals, all right? The range, what's the range? I heard negative 1 to 1, and they're included, right? So that's because sort of the far points here are 1, 0, 0, minus 1, 0, 1, minus 1, 0, right? So you can, you know, put this unit circle in a box, right? Certainly we have that the absolute value of sine theta is between 0 and 1, and 0, right? Or, if you don't want me talking about, and I apologize to the people not here, for I just used the invisible chalk. I'll go back to the one they can see. Of course, if you unwrap this, this is minus 1 less than or equal to sine theta, less than or equal to 1, and minus 1 less than or equal to cosine theta, less than or equal to 1. So to me, those are the most important basic facts about sine and cosine, that they go between plus and minus 1. That is very, very instructive as I try to graph them, right? It says that's kind of like they're stuck between those, you know? So here's the graph of sine. Let's see here. So I'll track some points. Sine of 0 is 0, right? Sine of pi over 2 is 1. All right, so we start out at, I'll make it yellow. Start out at 0. At pi over 2, we're up here at 1. What's sine of pi? Sine of pi, the y-coordinate here is 0. So sine of pi is 0. Sine of 3 pi over 2 is minus 1. And sine of 2 pi is, again, 0. Now, if we go backwards, and we can put some other things in, like if we go pi over 4, we're at about square root of 2 over 2, right? 0.7-ish. So it's kind of like this. You can throw in some points like that. Going back, if you sweep to minus pi over 2, you've got sine of minus pi over 2 is minus 1, right? So remember, sine is an odd function. And what else did we learn? Cosine was a even function, right? So anyway, to the limits of my artistry, it looks something like this. And of course, it goes on and on, right? Now, sine is an example of a periodic function, right? This is a periodic function. What's periodic function? A periodic function is one for which f of theta plus p, well, let's say well, fine, I'm using theta, so let me put x instead. Like, we don't have to use theta, we can use x. F of x plus p is equal to f of x. All right. For all x in the domain of f. P is assumed to be positive, right? So what's the period? And it's also typically assumed that you make p as small as possible. All right. So like, what's the period of sine? I mean, think about the coterminal angles, right? If you go 2 pi around, you're back where you started. You got the same sign. So the period of sine is 2 pi. Sine it repeats itself 2 pi. If I actually just gave you this much, right? This first cycle of sine right here. If I just gave you this much, and I said, this is a function, it has period 2 pi. You could draw the rest of the graph. You could just keep repeating it before and after. That's the idea. All right. Now, how about cosine? What's the graph of cosine look like? So this, again, this is y equals sine theta. So cosine theta, a little bit different, right? What's the cosine? Well, what was the relation we found about the coterminal angles? Do you remember? How did that go? I don't want to mess up the sign, like SIGN. Give me a second here. Come on. Let's see here. Oh, that's kind of complicated. Yeah, cosine of theta. Sine of pi over 2 minus theta. So, do you guys remember how we can do transformations of graphs from last semester? Remember how that goes? Well, first of all, remember sine is odd. So this is the sine, this is an algebra step. This is minus theta minus pi over 2, right? See that? Just pulled out the minus. Now sine is odd, so I can pull the minus out of sine. So can you describe to me if this, how can we get this from the graph of sine? How is y equals cosine theta related to y equals sine theta? See if you knew. Did you guys study transformations of graphs and precalculus? Did I do that? Were you in my precalculus? I did that, didn't I? I don't remember either. Curses. We should study that. It matters.
Like the slides and the flips.
Yes, the slides and the flips. So
We probably did that.
here, I'll just quick review up here. And I'll do it in terms of y and x. If y equals f of x, right, then y equals f of x minus c. This is a shift right by c. And if you have y equals, let's say, g of x, and you change it to y equals minus g of x, that just flips the graph over the x-axis, right? So we could figure out the graph of cosine by shifting the graph of sine pi over 2 to the right, right? So here I'll shift it pi over 2 to the right. I need to erase this. So let's see here, if I shift it pi over 2 to the right, I really need some graph paper up here. So this would be y equals to the sine of theta minus pi over 2, all right? So here, this is pi over 2, minus pi over 2, minus pi, pi over 2, pi, 3 pi over 2, 2 pi, right? Now that's not cosine. What do we also have to do? Flip it over, right? If we follow this idea, to get cosine from sine, we shift to the right by pi over 2, and then multiply by minus 1, which just flips the graph over. If I'd been smarter, I would have drawn some vertical lines to keep these on the same scale. Oh, well, it's too late. Anyway. Roughly speaking. There you go. That's y equals cosine. Now this is, of course, minus pi over 2, pi over 2, 3 pi over 2, 2 pi, so forth. And of course it goes on and on, right? Now, I am not suggesting that you memorize sine and then every time you graph cosine, think through this process. That is certainly not what I do. I just wanted to take a walk down memory lane and remind you that we can create one graph from another by doing these shifts and flips. If you know about that, that is a way to supplement your understanding of Chapter 6, because you can see a lot of transformations of graphs there if you look for it, okay? But, of course, I think this graph right here, we could also easily see from the unit circle, right? Theta equal to 0, we're at 1 for the x. Theta gets to pi over 2, x is at 0. Theta gets to 3 pi over 2, x is at 0 again. Excuse me. At pi, this is pi, not 3 pi over 2, what's wrong with me? At pi, the x is at minus 1, right? And at 3 pi over 2, the x is at 0. And at 2 pi, of course, we're back again. Cosine of 2 pi is 1. All right? So those are the basic graphs, sine and cosine, all right? You need to memorize those, I think, for best results going forward. You should know those. Like, somebody asks you to graph sine or cosine, you ought to be able to just write it out. It is in your best interest to memorize this, because it comes up over and over and over again in Calculus 1, and Calculus 2, and Calculus 3, and differential equations. Every single math class that you take past this point will involve sine and cosine and their graphs. Because understanding the graphs of sine and cosine is how we do analysis on them. You want to answer a question about where is sine equal to a half, right? If I want to, just to give you an example. Solve sine of theta equals to a half, right? So graphically, here's how you do that. Sine is this guy, right? Starts at 0. I don't worry so much about the spacing. All right? And what's a half? Y equals a half is this. Right? Where the intersection of sine graph and the y equals 1/2 graph happen, those are all the solutions of sine theta equals to a half. There are infinitely many. So, for example, this one, we know from right triangle trigonometry that sine theta equal to 1/2 has solution pi over 6, right? I'll do 30 degrees, since you guys have an easier time thinking in degrees. 30 degrees. Sine of 30 degrees is a half, right? So what else does that mean? That means that sine of what? Sine of 390 degrees is also equal to a half, right? In fact, the sine of 30 degrees plus 360 degrees times n is equal to a half for any n in the integers. You guys know integers, right? 0, plus or minus 1, plus or minus 2. I don't think I talked about that this semester, did I? No. Yeah, it's odd. I almost always start every class with that. Here I followed the book. Felt wrong. Anyway, so there are infinitely many. Now, are those all the solutions? They're not, right? These are just these ones. Boop, 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 boop. Boop. It's on the upswing, right? Boop. The one's on the upswing. How about these? What are those? How do you find those solutions? Well, if we understand the symmetry of the graph, we can figure it out, right? Tell me, this is what? This is 180 degrees, right? And so the symmetry here is that's as far away, the x is as far away from 0 as the circle is away from 180 if I made my graph real clean. So you said 150, exactly right. So the other kind of solutions is that the sine of 150 degrees plus 360 degrees times n is also equal to a half. That's it. There's these two infinite families of solutions for sine equal to a half. So if I ever ask on a test, find all the solutions of sine theta equals to a half, right? You should expect the answer is like an infinite set. You'll have to use either some kind of like listing to formulate your answer, like a comma dot 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 kind of thing, or you'll have to introduce an integer to describe the indexing of the solution set. Now, oftentimes, so that I don't have to grade that because it never turns out well, I will just say find the solution of sine theta equals to a half that's between such and so forth an angle, right? So if I narrow the scope, there might just be one answer, you know? But my point to you is understanding the graph of sine, having command over it, allows you to solve problems like this very easily. And if you really thought about it without the graph, I think it would be much harder. So what we're about to get into is how would you graph something like this? You know, so we'll be doing stuff like that next time. Like how do you graph modified sines? And so what we're going to do is use the idea about transformations of graph to, like, you know, shift it pi over 2 to the right and then stretch it out by a factor of 3. We'll talk about the amplitude. What's the amplitude? It's like how far it goes up and how far it goes down. Like the amplitude of sine and cosine is 1. The amplitude of that one would be 3. Anyway, so hopefully we'll talk about that Friday. I'm hoping I feel better Friday. If I don't feel better, I will make a video because I'm going to take that home with me. I'm not coming to school tomorrow because I already know.